So here the given question is a cylindrical conductor of radius r is carrying the constant current. The plot of the magnitude of the magnetic field B with a distance d from the center of the conductor is correctly represented by the given figure. There are four figures given. Which one of the following is the right figure? We are going to analyze in detail. First, we can draw the given diagram. The cylindrical conductor of radius r. This is a cylindrical conductor. Its radius is r. So cylindrical, we got to extend that cylinder. So here it's a complete diagram. It is carrying the constant current I. It's not varying current. It's a uniform current D. It's constant current. I, the plot of the magnitude of the magnetic field B with the distance d from the center of the conductor. Suppose if you are taking from this is the center of the conductor at a distance d radially out, how the magnetic field vary each and every point. Even if you are taking here, this conductor is extending along this way. So from the center of the conductor along the radial direction d inside the conductor as well as the outside the conductor, how the magnetic field is looking like that. This is the thing we are going to discuss now. So for this one we are going to use the formula that Ampere circuit law. So first we need to write the Ampere circuit law. Ampere circuit law. It says integral over the closed integral over B dot dl. So along the line of circle, the magnetic field that would be equal to mu naught times the I. This is the Ampere circuit law. Here I enclosed. That means suppose if you are taking the for example, this is a circle, this is a line integral of the magnetic field. The current is enclosed within this circle is I enclosed. So that integral over line, it will be equal to mu naught times the I enclosed. This should be the Ampere circuit law. Now first we have to analyze this Ampere circuit law inside the cylindrical conductor as well as the outside. So first we can take the distance. The first case is less than the radius of the cylinder. We are going to analyze. That means from the center, this is O is a center, here R is a radius. In between these two, what is the magnetic field variation due to the current carrying conductor? We know the from the Ampere law, any current carrying conductor, it will produce a circulating magnetic field according to the right hand thumb. If your thumb is pointing the current direction, the curled finger represents the magnetic field direction. Still, here also it will form like that. The current is passing through the cylindrical axis of uniform current I, constant current. So it will generate the circulating magnetic field. So circulating magnetic field produced along the direction of the motion of the current. So that is the thing we are going to analyze now. But here we are going to apply to find the magnetic field at any distance t less than r. We are going to apply the Ampere circuit law. So integral over the closed integral B dot dl is equal to mu naught times I enclosed. Now we are taking the circle. Suppose take this circle at a distance d. From the center O, I am going to take the circle at a distance d. Even here, everywhere we are extending this radius here. So suppose here, if you want to represent, like we can take along this circle from the axis of the circle, axis of cylinder, the circle distance is the circle radius is d. So the B is along the circle at a distance d on the circumference of the circle. The magnetic field is constant at a distance d. So this you can take it out. B, if you take it out, integral over dot dl. The line integral goes from 0 to 2 pi d, because the length of the circle here, it's a line integral. If this is a starting point is 0, the length of the circle is here, it's 2 pi d. The circumference of the circle is the total length 2 pi d, that would be equal to mu naught times the I enclosed within the circle. We can call it's I prime, because we don't know how much amount of current flowing inside the circle, that is the I enclosed prime. So here anyway the left hand side part is easy, b dot. If you are taking this integral, it will give L over 0 to 2 pi d is equal to mu naught times I enclosed. Now if you are substituting the upper limit, it will give b 2 pi d mu naught times I enclosed. So anyway, this left hand side part is easy, but we don't know what is the current in the enclosed part. This is our circle, the Amperian loop. We can call this is the Amperian loop. This is a magnetic field loop due to the current inside the loop. So this magnetic field loop, how much current is enclosed? That is the question we have to ask. So for finding the current inside this circle of radius d, we are going to compare the current density with the bigger circle of radius r with the smaller circle of radius d, because anyway current density everywhere is constant. So we can call the current density in general we are using the symbol J to represent the current density. This current density is constant, that means the current density of radius or enclosed this bigger circle, that would be equal to the current density at radius d enclosed within this small d. So a small d circle of radius d, this circle, the current density here as well as the bigger circle, the both if we are calculating in the both area, the current density will be constant. That is the case. Anyway, the density, what is the density of the current means the current flowing per unit area, that will be constants even if you are taking bigger circle or smaller circle. For bigger circle of radius or the current density, you can define the total current passing through the cylinder, that is biggest circle containing the whole cylinder. That current density is equal to current divided by the area pi r square divided by the smaller circle of radius d. This is a smaller circle. That current density is equal to I enclosed. The current enclosed within this circle, already we defined it is I enclosed prime divided by the radius of this circle having the area pi d square. So we need the unknown current I enclosed within the radius d. So you can keep that in one side, I enclosed prime. If you are pushing this pi d square to the other side, it will goes to the numerator into I divided by pi r square. You can cancel pi. So I enclosed prime, that would be equal to I d square divided by r square. This much amount of current passing through the radius of the circle d, the smaller circle d. So this much amount of the current. Once if you know the capital or small d, then the constant current d, the cylindrical carrying the constant current I. Once if you know these three quantity, then we can find how much amount of current enclosed within the radius of circle d. So that we can calculate. Now we can substitute this one here. Now we know the I enclosed prime, therefore the b, that would be equal to, if 2 pi d goes to that side, it will goes to the denominator 2 pi d. I enclosed here is I times d square divided by r square. So b is equal to, you can cancel 1d. So I divided by 2 pi r square into d. So this is a current enclosed inside the cylinder. This is the amount of magnetic field inside the cylindrical radius of D. Suppose if D is less than the magnetic field varies linearly with the radial distance D. That means magnetic field, because I current is constant, 2 pi capital R is constant, so you can remove this constant by making the proportionality B is proportional to the radial distance D. If D is increases, B increases. If you are measuring the magnetic field from the center, it will keep on increase. Suppose if here it is 1 Tesla, here it is 2 Tesla, 3, 4, 5, 6. So it will linearly increase. That is a thing here. It is represented by the equation. B is proportional to the radial distance D. Now we are ready to analyze the magnetic field outside the circle, how it will be vary along with the radial distance. So to find this one, now we are going to use again the Ampere circuit law. The second case, when the radial distance is greater than the radius of the cylinder, we are going to use the Amperian circuit law, integral over B dot dl is equal to mu naught I enclosed. So anyway, if we are taking any Amperian law, suppose if this is a cylinder, we are just going to analyze outside the cylinder along the radial distance D. This along this line of circle, the magnetic field everywhere is constant. So you can take outside the integral. So it will come out because magnetic field is constant everywhere. Integral over, again the integral goes to 0 to 2 pi d, because we are going to take the line integral. That means we are going to calculate the length of this circle. So it will, suppose if we are taking reference point any point 0, the length of the circle represents the circumference. So the line integral will go from 0 to 2 pi d times dl is equal to mu naught. Now the enclosed current is inside. Now the Amperian loop is outside the cylinder. The total current enclosed within the circle is the current enclosed inside the cylinder, that is I, that is constant. Now you can cancel this integral d, so L will be there. Again, if you are substituting the upper limit, we will get B times 2 pi d equal to mu naught I. So B equal to, if you are pushing this 2 pi t to the other side, mu naught I divided by 2 pi d. So B, if you are taking, mu naught is constant, here I is constant, 2 pi is constant. The only the thing we have to vary the radial distance 1 by d. Now we can conclude this is a constant. By removing this constant, you can make this equal sign proportionality. B is inversely proportional to the radial distance d. So whenever the measuring distance d, the radial distance d, the magnetic field is inversely proportional to d. As d increases outside the cylinder, the magnetic field will keep on decrease. So suppose if you are measuring outside, if here it is 10 Tesla means here it's 9, here it's 8, it is inversely, it will vary inversely. That is the meaning of this one. Now we can draw this graph. Suppose if you are taking the y-axis as magnetic field, the measurement axis, x-axis is the radial distance. Here there are separatrix. The radial distance d equal to r. That means 0 to r represents the inside the cylinder, how the magnetic field variation will be there. R to d, this portion represents the outside the cylinder. The outside the cylinder, the B is inversely proportional to D. This is a separatrix. So this portion represents inside cylinder, this portion represents outside the cylinder. So inside the cylinder, B is proportional to D. Already we derived that expression. If you look at this expression, B is proportional to D. That means it's linearly will vary with respect to the radial distance. That means it's a linear graph. B versus D graph is linear graph. Hence, the graph will be linear up to the radial distance d. is D increases, then B also will increase inside the cylinder. This portion represents the inside the cylinder, the magnetic field versus the radial distance variation. Now, outside the cylinder, just now we derived, this is B is inversely proportional to D. As D increases, magnetic field will decrease, but it will be, the graph will be looking like that. It's inversely. So, here outside the cylinder, B is very inversely proportional to D. This is inside the cylinder, this portion B is proportional to D. So this is the best graph represents whenever the cylinder carrying the constant current I, the magnetic field variation along the radial distance inside the cylinder as well as outside the cylinder. This is the best graph. From the above discussion, the first one, second one, it is wrong. Inside the cylinder, it is linear 0 to R. Outside the cylinder is 1 by the distance. So the right figure is the option 3.